So last time we looked into the formal definition of entropy in terms of number of microstates. But entropy is Boltzmann's constant times logarithm of number of microstates. Or usually we describe this as number of accessible microstates, in the sense that there might be some microstates that aren't currently possible, so we wouldn't count those. But the entropy is really just measuring the number of microstates modified by logarithm and Boltzmann's constant to make the numbers more convenient to work with. And that means entropy is really just a description of how many ways something can be arranged, how many ways something can happen. If we say the entropy has increased in a system, we really just mean the system has changed in a way that involves more microstates. More entropy just means more microstates. And more microstates means more likely to happen, higher probability. So entropy is intrinsically tied to probability in this way. Higher entropy means that the system is currently arranged in a way that involves more microstates. That's more likely to happen because probability is proportional to number of microstates. We can also look at this in terms of a change, because usually we don't care about how much entropy a system has, we care about how the entropy is changing. So if you write out a delta S, delta entropy, how do you calculate delta anything?
Final minus initial.
If we just write out final value minus initial value. And we can express each one of those as Boltzmann's constant times logarithm of number of microstates, final number of microstates, and initial number of microstates. But it's the same KB, the same Boltzmann's constant for both, so we could just factor that out. And say this is just Boltzmann's constant times logarithm of final number of microstates minus logarithm of initial number of microstates. And now we can use some of the magic of logarithms. What can you do to combine these? If you've got a logarithm minus a logarithm, same base, just different inputs, how could you combine those into one logarithm?
You divide them.
Yeah, we can just divide what's inside. Boltzmann's constant times the logarithm of the ratio of final number of microstates over initial number of microstates. So that's the change in entropy. And this becomes much more convenient to calculate because the number of microstates might be some colossally huge number. But if the number of microstates is changing by, let's say, being multiplied by 10, the change in entropy is going to be Boltzmann's constant times logarithm of 10. Because the ratio of the initial amount versus 10 times as much would be 10 over 1. So this works really well with ratios. If the entropy is being changed by being multiplied by some factor or being divided by some factor, delta S becomes much more convenient to calculate because it's defined in terms of logarithms. Any questions on that so far? And this is really one of the most powerful things about logarithms. Logarithms change division of what's inside to subtraction of what's outside, and vice versa. Subtraction of what's outside into division of inside the logarithm. So it works really nicely with ratios. And this is really the reason, anytime you've got some quantity defined in terms of a logarithm, whether it's entropy or Richter scale for earthquakes is defined in terms of a logarithm, loudness of sound in decibels is defined in terms of logarithms. I think pH is also defined in terms of logarithms. The reason all these things are defined in terms of logarithms is specifically to make these ratios work out to differences. It makes the numbers much easier to work with in those cases. So that's delta entropy. Delta entropy, which again is usually what we actually care about, is this ratio of final microstates to initial microstates. Any questions on that definition so far? However, even though that's how entropy is defined, this is what entropy actually means, a measure of how many ways there are something could. This is not usually the most convenient way to actually calculate it, because you wouldn't want to have to count up the number of microstates. In this context, you don't really need to know how many microstates, you just need to know how the number is changing. But even that can be really inconvenient to work with. Like if you're dealing with just flipping a bunch of coins, it's easy enough to calculate how many ways there are that could happen. But if you're dealing with a system like 10 moles of hydrogen and you want to know how many ways there are for energy to be distributed amongst those 10 moles, these numbers are going to be ludicrous to work with. So instead, we use some simpler versions. Some other formulas that end up being equivalent, but are much easier to work with in the thermodynamics situations. Specifically, based on the idea of adding heat to a system. If you've got some gas, or any substance really, but let's assume it's a gas, and you add heat to it. You add heat to it, so you're giving the gas more energy. What would you expect to happen to the number of ways the energy could be arranged if it now has more energy than it did before? Because remember, this energy could be divided amongst the molecules in many, many ways. We're assuming that evenly distributed is most likely, but there's many ways it could be distributed. What happens to the number of ways it could be distributed if we're adding more energy to the system? It's going to increase. More thermal energy, because we've added heat, directly leads to more ways that energy could be distributed. That means larger number of microstates, and that directly means higher entropy. So adding heat directly increases the thermal energy. And work is a little different. If you add work, you're also increasing the thermal energy, but by adding work, you're squeezing the gas into a smaller space. So if you add work, you're squeezing the gas into a smaller space. That means there's less places the gas could be, fewer places the gas could be. So adding work means you're increasing the thermal energy, but you're also restricting the motion of the molecules. Increasing energy would suggest more entropy because there's more ways the energy could be arranged. But restricting the space it could move in decreases entropy because you're adding in extra boundaries, extra barriers to the motion. And for work, those end up canceling out. Work itself does not change the entropy, but heat does. Adding heat gives the gas more energy to play with without changing the size it's in. So adding heat directly increases the entropy. And in fact, those are directly proportional. Change in entropy is directly proportional to heat. Add heat, you increase the entropy. Remove heat, you decrease the entropy. No heat at all, you're not changing the entropy. At least in the case of a gas in a container. Any questions on that so far? That means, if they're proportional, that one of them has to equal something times the other. And it turns out that that something is in fact 1 over temperature. Because let's say you add a certain amount of heat to a system, to an object. Proportional to internal energy, not in this case, because the internal energy could be changed by work or heat. Doing work to the system changes the thermal energy, but it does not change the entropy. The change in entropy is specifically caused by heat flow. If you add heat to the system, you're increasing the entropy. If you remove heat from the system, you're decreasing the entropy. Because heat directly changes how much energy there is available, but it doesn't change the amount of space the gas takes up. Work changes the amount of space. So delta U equals heat plus work. The heat is what changes the entropy. And of course, if it's an isochoric system, if there's no work at all, then heat and delta U are basically synonymous. But work also plays a role in delta energy, but work does not play a role in entropy in this context. So we want to look at just heat alone. And the reason we have it divided by temperature here, if you consider two systems, let's say you've got one very cold system and you add, let's say, 100 joules of heat, versus one very hot system and you add 100 joules of heat. And you compare what's going on there. If you've got a very cold system, cold gas, and you also have a hot gas. And let's say we're applying the same change to both of them. So let's say we add 100 joules of heat to the cold gas, and we also add 100 joules of heat to the hot gas. It's the same amount of heat, but why would we expect these to be different changes in entropy? Why would the same amount of heat lead to different changes in entropy just because the gases are at different temperatures? Any thoughts on that? Yeah, this is still all about the number of possible microstates, the number of accessible microstates. If we're looking at microstates as, and in this case, we're really talking about how energy is distributed. So number of microstates is how many ways the energy can be distributed to all these molecules. We're adding the same amount of energy, but what do you know about the amount of energy that's already there? If you got this gas is cold and this gas is hot, what does that suggest about how much energy they already have? Assuming it's the same amount of gas. In fact, let's just assume this is standardized. Let's say we've got exactly 1 mole of cold gas and exactly 1 mole of hot gas. Yeah, the hot gas is going to have a much higher energy. The hot gas already has lots of thermal energy. Cold gas only has a little thermal energy. In fact, let's just make up some numbers. Let's say the cold gas has, let's say, 100 joules of thermal energy already. And let's say the hot gas has, let's say it's at a 10 times as much temperature and it has 1,000 joules of thermal energy. If this gas has 100 joules of thermal energy right now, Q is the amount of heat being added. So the thermal energy is the amount of energy this already has. Heat is the amount of new energy being added. So keep that in mind. Heat doesn't represent the amount of energy it has. In this context, heat represents the transfer of energy. When we say heat is 100 joules, we're saying we're adding 100 joules of new energy to the system due to a temperature gradient. So if this system already has 100 joules of energy, and we add 100 joules of heat, how much is that changing the energy it already has? Think in terms of ratios or proportions. If it starts with 100 and you add 100 more, what have you done to the amount? Yeah, you've just doubled it. That's an enormous change. It's a very large relative change. Very large change relative to what it's already got. But in this case, it's got 1,000 joules already. You add the same 100 joules, but that extra 100 joules is pretty small compared to what it already has. A relatively small change. It's only increasing it by an extra 10% rather than doubling it. So even though we're adding the same absolute amount of heat, 100 joules here, 100 joules there, 100 joules added to a cold gas is comparatively a large amount compared to what it's already got. 100 joules added to an already hot gas is a small amount compared to what it's already got. So we expect this same amount of heat added to a low temperature means large change in entropy because we're adding comparatively a large amount of new energy to play with. Same amount of heat added to a gas with high temperature, so same heat but a larger temperature, leads to a smaller change in entropy because adding an extra 100 joules to something that's already got lots of joules isn't much of a change. So high temperature already means heat added means a small change in entropy. If it's at low temperature already, heat added means a larger change in entropy. So this is why we have a divided by temperature here, to account for the fact that the temperature makes this difference. It also gives us the right units of measurement. Heat's measured in joules, temperature is measured in kelvins. Joules per Kelvin is the same as the units of Boltzmann's constant. So it's the same as the way we define entropy in the first place. But I guess it's really the other way around. We're using Boltzmann's constant here because we want joules per Kelvin to match up with this idea. But in both cases, entropy works out to joules per Kelvin or kilojoules per Kelvin because we're often talking about fairly large changes. Any other questions on that so far? So again, even though this is how we define entropy, this is what entropy means, the way we're often going to be calculating it is based on heat divided by temperature. So this is often a more practical formula. If you want to actually calculate entropy, in most cases, we're going to be using heat over temperature. So you can use this in any situation where you're adding or removing heat to an object at a certain temperature. If you know the amount of heat added or removed, and if you're removing heat, you just treat heat as a negative value, and you know the temperature, divide those, and that tells you the change in entropy. Any questions on that so far? And we could even calculate how much entropy, let's try an example, just calculating how much the entropy is changing in a certain circumstance. Let's say we are maybe freezing some water. Let's say you've got a cup of water. Let's say half a kilogram of liquid water. And for simplicity, let's say it's already at the freezing point. Temperature equals 0 degrees Celsius. And you want to freeze it. It's already at 0 degrees. To freeze it, though, what do you have to do to it? If you want it to freeze, what do you need to do? How do you freeze some water? You got to lower the, well, you're not lowering the temperature yet, though. If the water's at 0 degrees, it's already at the freezing point. When you freeze it, it'll still be at 0 degrees. Yeah, we want to lower the bond energy, which means we've got to have heat flowing out of it. We've got to have heat flowing out. Of course, that heat doesn't just vanish. It's got to go somewhere. Where does that heat go to? If you just want heat to leave the water, what's the the environment around it, right? Presumably this is surrounded by air. So the water is losing heat, and presumably the air around it is gaining that heat. But heat naturally only flows from what to what? From hot to cold, yeah. So presumably, in order for heat to flow from the 0 degree water to the air is going to have to be even colder. Let's say the air is at a temperature of Let's say we put the air at -10 degrees Celsius. So if the water is currently at 0 degrees and the air is at -10 degrees, heat is going to flow from the relatively warm water to the relatively cold air. And let's say we just wait until this is completely frozen. Wait until the water is all frozen. So the final situation is going to be the water still at 0 degrees because we're just waiting until it's just barely frozen. We're not waiting any longer. So we wait until the liquid water becomes all solid, but still at 0 degrees, and then we stop the experiment. And we want to figure out what's the change in entropy involved here. We can do this, but first we need to figure out how much heat. How could we figure out how much heat has to flow to make the water all freeze? If we're talking about the heat involved for the water, the heat that has to leave the water. Yeah, that's m delta H, because we're still talking about a delta E bond. The heat traveling is delta E bond. And you could even think of this in terms of just treating this as an open system. You've got bond energy decreasing because heat is leaving. So delta E bond is, usually we write work plus heat, but there's no work, so it's just heat. We can use our usual delta M, delta H formula. And what would we write for delta M here? .5 kilograms. One thing we got to be careful about though, which direction is this changing? Is this changing from solid to liquid or liquid to solid? Yeah, this is going from liquid to solid. So should we expect heat to be entering or leaving? Yeah, this should be a negative value. You can also see this from final and initial. If you write the delta M as final mass minus initial mass, that's specifically final and initial mass of the higher energy state, the higher phase. Between solid and liquid, liquid is the higher state, the higher energy state. So this is specifically final mass of the liquid minus initial mass of the liquid. How much liquid did we start with? Yeah, we started with 0.5 kilogram. And assuming it all freezes, how much liquid will we end with? Right, 0 kilograms. So final minus initial amount of liquid is going to be 0 minus 1/2. That's -1/2, which corresponds to the idea that we should expect heat to be leaving the system to make this happen. So -1/2 kilogram is the delta M. And where would we find delta H? Yeah, we can look that up on a data table. I happen to have one right here we could use. So delta H for water freezing, heat of melting then, would be 333.5 kilojoules per kilogram. Multiply that out, and that'll tell us the amount of heat necessary. So half of 333.5 negative 166.5, or 166 point, I'm just going to round that off to negative 167. And that'll be kilojoules as the amount of heat leaving the water. And now what do we do with that? If we want to know the change in entropy for the water, how could we convert this heat into a change in entropy? Yeah, change in entropy is heat divided by temperature. And note that that's not heat over change in temperature. That's specifically the heat we added or removed divided by what the temperature is right now. Heat we know is negative 167 kilojoules. And what's our value for temperature here? Yeah, we do need to use Kelvin here. If you were using a delta temperature for some other formula, then Celsius is okay as long as you're consistent about it. But since this is just temperature, not delta temperature, this must be in Kelvin. And I think that's probably easiest to see in this specific case, because if you try plugging in 0 degrees Celsius, you get division by 0, and that doesn't make sense. So this has to be in Kelvin. 273 kelvins. Divide those, and I'm getting about negative 0.611 kilojoules per Kelvin. Since that's kilojoules, we could also multiply by 1,000 to make it joules. So about negative 611 joules per Kelvin. So that's delta entropy for the water. During this process, as the water freezes, the water is losing 611 kilojoules per Kelvin, or sorry, 611 joules per Kelvin of entropy. The water's entropy is decreasing. And going back to the original definition, what does a decrease in entropy represent? Yeah, fewer accessible microstates. It's happening because we're removing entropy. I wouldn't say a decrease in heat, or we're removing heat. Heat is not decreasing, heat is being removed, which means the energy is decreasing. But the important thing in terms of the original definition is the microstate, the number of microstates is decreasing. We're getting fewer microstates because there's fewer ways for this to exist. We're both removing energy. Less energy means there's fewer ways for the energy to be arranged. And also in the process of freezing, we're forming bonds. We're making these molecules, instead of being able to move around more freely, they're more locked in place. So anytime you make a system less free to move around, that's a decrease in entropy. You're reducing the number of ways it could be arranged. And also removing heat from the system reduces the number of ways the energy could be arranged because there's less energy available. So forming bonds, lowering the amount of energy of a system, lowering the freedom of movement of the particles, that's going to be increasing entropy, or sorry, decreasing entropy. Extra restrictions means lower entropy. But if you allow more freedom of movement, if you remove barriers, if you break bonds, if you add more energy to the system, allowing more freedom of movement, more ways things could be arranged, that involves an increase in entropy because you're allowing more ways it could be arranged. And someone was asking about temperature. Yeah, the water is definitely staying at a constant temperature because it's only going through a phase change during this process. Phase change just means that the bonds are breaking or forming, but there's no change in temperature. And that heat is being dumped into the air. So the air is raising its temperature. The heat that the air is gaining becomes thermal energy because the air is not changing phase. But the thing is, if we're assuming there's lots and lots of air, presumably this is a fairly small amount of water and a whole room full of air, or maybe this is even outside and there's even more air. So we're assuming that there's so much air that the temperature is not changing very much. In fact, let's make a note of that. Let's say lots of air. So the temperature is at negative 10 degrees and mostly stays at negative 10 degrees. It increases very slightly, but let's assume it's only increasing just a tiny amount, not even enough to notice on a thermometer. So the air effectively stays at negative 10. And is that the meaning of accessible and inaccessible microstates? Basically, yeah, accessible in the sense of possible. Like there may be many ways a system could be arranged, but maybe only some of those ways are possible right now. For example, maybe these molecules could be moving anywhere, but they're bonded, so they have to be near each other. That would be an example of a limitation on this idea of accessible microstates, that the microstates where they're far apart are not accessible because those molecules are bonded together. They can't go far away. Or maybe you've got, let's say, a room with maybe clean air on one side and smoke on the other, and there's a wall between them. With that wall there, these smoke particles can't exist on the other side of the room. But if you remove the wall, those smoke molecules could now be anywhere. So by removing the wall, you're increasing the number of accessible microstates, because smoke molecules on the other side of the room is not accessible if there's a wall in the way. Remove the wall, you unlock more possible, more accessible microstates. So that would be an increase in entropy by removing a barrier, allowing more freedom of motion. Putting the barrier back in is going to reduce the entropy somewhat because you're reducing the freedom of motion, but it's not going to reduce it back down to the original amount, because it's not like you're condensing all the smoke back onto one side of the room when you put the wall back. So removing the wall increases the entropy drastically. Putting the wall back in decreases the entropy somewhat, but not anywhere near back down to the original level, because the smoke is already out of the bottle, so to speak. Any other questions on that so far? So it looks like the water's entropy has decreased. We've reduced the number of microstates. We've reduced freedom of motion by freezing it, bonding the particles further or closer together. And also we've removed energy, meaning there's less energy available to be arranged. So definitely the water is decreasing entropy. But the problem is the first or second law of thermodynamics says that shouldn't happen. First law of thermodynamics is just conservation of energy. Change in energy equals heat plus work. The second law of thermodynamics says that under certain circumstances, entropy should not decrease. But we see that the water here is decreasing its entropy. How is that possible? What else is happening that allows the water to decrease its own entropy? Yeah, the air is gaining entropy. We're removing heat from the water, so the water's entropy decreases as heat leaves. But that heat doesn't just vanish. The heat enters the air, so the air's entropy is increasing. And as long as the air's entropy increases as much as the water's entropy decreases or more, then the total entropy won't be decreasing. And total entropy of a closed system is really what the second law of thermodynamics is talking about. In a closed system, the total entropy does not decrease ever. Not because it's physically impossible, but again, going back to probability. The probability of entropy decreasing in a closed system is so ludicrously small that if this were a math class, I would say the probability rounds off to zero, but for all practical purposes, the probability of entropy decreasing in a closed system is zero. It's never going to happen, at least if the system is large enough. If you're talking about something very small, like just a couple of molecules, then you do have that extra randomness involved. But for a large system, like anything on the scale of like a mole or something, or even if it's just like a few million molecules, something extremely small like that, the probability of entropy in a closed system decreasing is so small that it may as well be zero. So let's verify that. Let's check the entropy change of the air and make sure that the second law really holds. That entropy overall is not decreasing. For the air, we're assuming the air is staying at relatively the same temperature. We're assuming that the air's temperature doesn't change much. Presumably it is going to rise a little tiny bit, but we're assuming there's so much air that its temperature does not change much. So there's just a single value of temperature. And what about heat? How can we figure out how much heat the air is gaining? Where's the air getting its heat from? Yeah, the heat that the air gains is just the heat that the water lost. So they're going to be exact opposites. Heat of the air is going to be the opposite of heat of the water. The water was losing 167 kilojoules of heat, so the air is gaining 167 kilojoules of heat. So that's the heat for the air. And then how do we change that into a change in entropy? we can just take the heat divided by temperature. So that's positive 167 kilojoules divided by, and what temperature should we use for the air here? Yeah, negative 10 degrees converted to Kelvin is 263 Kelvin. You just add 263 or 273. So 167 divided by 263 is 0.635, and this will be positive kilojoules per Kelvin. Or converting to just joules per Kelvin, multiply by 1,000, so we get positive 635 joules per Kelvin. So during this process, as the water freezes, the water is losing 611 joules per Kelvin worth of entropy, but at the same time, the air is gaining 635 joules per Kelvin of energy, or entropy. So since the increase in entropy for the air is larger than the decrease in entropy for the water, what does that tell us about the overall entropy of the whole system? Yeah, the overall entropy is increasing. So I would say the delta entropy is positive, the entropy is increasing. In fact, we could even find delta S here, total here. If you wanted to know the total delta S of the whole system, we would just add these together. Positive 635 plus negative 611 would be positive 24 joules per Kelvin. So that would be the total change in entropy of the system. It's a small change overall, but it is positive, and that's the important thing. Overall, the entropy of this system is increasing. Delta S total is a positive value. And this is what the second law of thermodynamics is talking about. In any closed system, in this case, air and water combined, the total entropy will not decrease. It might stay the same, it might increase, but it won't decrease. If you find that the total entropy is decreasing, something's gone wrong. Either something in the algebra has gone wrong and you need to redo that, or if all the algebra is correct, total entropy decreasing tells you that process won't actually happen. One example here would be, let's say you have water at 0 degrees, air at negative 10 degrees. If heat flows the other direction, would you expect this to happen in real life? No, this doesn't make sense. Heat's not going to flow from the cold object to the hot object. And so far, we've just been taking that for granted. Of course, heat flows from hot to cold. That's what heat does. But mathematically, the reason for that is if you actually try running these calculations for this process, if you assume that heat flows from the air to the water, from the cold object to the hot object, if you actually run the calculations on this, you'll find that the air is losing 635, the water's gaining 611, and the total change would be negative 24. Everything would just be completely reversed. So the reason why heat can't flow from cold to hot is because that process involves entropy decreasing overall in a closed system. And that's not going to happen according to the second law of thermodynamics. So heat flowing from cold to hot doesn't happen because entropy can't decrease in a closed system. If it's an open system, anything goes. It's certainly possible to make heat flow from cold to hot. In fact, this is how a refrigerator works. You're taking the already kind of cold food and pulling more heat out of it to make it even colder and dumping that heat into the air around the air outside the refrigerator, which is already warm. So you can make heat flow from cold to hot, decreasing entropy, as long as something else increases entropy even more. So this is the foundation of things like refrigerators, air conditioners, anything that's making heat flow from an already cold object to an already hot object to make the cold object get even colder. That's done by making the entropy decrease locally, but making something else somewhere else increase entropy even more to compensate for that. For example, an air conditioner, you're cooling off the inside of the house a little bit and dumping lots of heat to outside the house. And this is all powered by a power plant, presumably burning some fuel, causing even more increase in entropy somewhere else. So any decrease in entropy somewhere, it's possible, but you have to increase entropy somewhere else even more to balance that out. Because in total, the entropy of the universe cannot decrease. Or to put it another way, you can't win, you can't break even. Those are sometimes how the first two laws of thermodynamics are phrased. Can't win, you can't get energy out of nothing. You can only get it from heat and work. Can't break even, the entropy can't be decreased. You're always going to have some increase in entropy. And I've sometimes heard the third law as you can't even quit the game, but I'm not entirely sure why that is. But that's the foundation of entropy. Any other questions on that so far? And a good way to get some practice with this, by the way, is to go back to some of the early conservation of energy problems we were looking at way back at the beginning of the quarter. All the stuff on thermal energy, bond energy. If you mix these two substances together, what's the final temperature? Go back to some of those problems and try calculating the change in entropy of each step. Like, yeah, you know, this ice is gaining gaining bond energy as it melts, or this lump of hot iron is losing thermal energy as it cools down. Take those changes in energy you already calculated and see if you can calculate the change in entropy associated with that. One problem though, this delta S is assuming that temperature is the same the whole time, which is the case here. This water is not changing its temperature because it's just changing phase. This air isn't changing temperature much because it's so large. But what could you do if the temperature is changing? Like, let's say the air is warming up from -10 to -5. You can't use -10 here because the temperature is mostly hotter than that. You can't use -5 because most of the time the temperature is colder than that. What would you do instead? How could you account for that? If the temperature is changing, if the temperature is not the same all the time, if it starts and ends at different temperatures, how could you have divided by temperature if there's not just one temperature the whole time? Like if you've got something changing from, let me put it in Kelvin for now. Let's say the initial temperature is 300 Kelvin and the final temperature is 310 Kelvin. If you calculate it at both instances, the problem is heat is not a property that the system has right now. Heat is the process happening over the course of some period of time. So you can't just take heat divided by one temperature and heat divided by the other temperature. But what you can do is you can treat it as almost like a constant temperature. If it starts at 300 and ends at 310, what's a single temperature that is pretty close to all those temperatures in between? Yeah, 305. We can say the average temperature, which you could calculate by looking at just what's halfway between, or more formally, add them together, divide by 2, 305 Kelvin. So one thing you can do, if the temperature is changing, as long as it's not changing a huge amount, you can approximate delta S by taking the average temperature. Delta S is approximately heat over average temperature. This is a very accurate approximation. It's not perfectly accurate, but it's very close to accurate as long as the temperature is not changing an enormous amount. So Q over T, if the temperature is constant, approximately Q over T average if temperature changes, but not very much. And if the temperature is changing a large amount, or if you need an exact value, you can use this logarithm formula. The exact value, if the temperature is changing, change in entropy is heat capacity of the object times the logarithm of the ratio of final temperature over initial temperature. And we can look into why this is the case next time, and also some examples of this. But this is another formula you can use if the temperature is changing a lot. And there's not really a hard boundary between changing but not much versus changing a lot. It's really just a matter of how much accuracy you want. If it's changing by just a few degrees, go ahead and use Q over T average. If it's changing by hundreds of degrees, use the logarithm formula. In between, you might try both and see which one is, I mean, this is going to be more accurate if the temperature is changing at all. But this is usually easier to use, and it's remarkably accurate for even if you're changing by like 50 kelvins or something. It's still very close to accurate. Any other questions on that? All right, have a good weekend, and I'll see you next time. You're welcome.